Ever scroll past some amazing visual effect online and wonder, how did they do that? Today we're diving into the world of shaders, the code that powers everything from subtle Instagram filters to mind-blowing video game graphics.
It's like having a secret language for talking directly to your computer's graphics card.
Okay, so no more magic spells. We're breaking down this excerpt from the Book of Shaders to understand how programmers create those mesmerizing, ever-shifting patterns and textures. Basically, if I'm getting this right, shaders give instructions to the GPU, telling it how to color each and every pixel on the screen.
Precisely. Instead of just saying, make this square red, shaders allow for incredible control over each pixel's color, creating smooth gradients, intricate patterns, or even realistic-looking materials.
That makes sense. You'd need that level of detail for this. Things like textures on clothing in video games, or those filters that make your selfies look like old film photos. It's like giving the computer a paintbrush instead of a stamp, right?
What's fascinating is that GPUs are uniquely designed for this kind of work. Unlike the CPU, which manages your computer's general tasks, the GPU is all about parallel processing. Imagine it like a massive art studio with thousands of artists, each working simultaneously on a small portion of the same image.
That's a powerful image. So while the CPU is busy juggling everything else, the GPU is solely focused on making those visuals happen with lightning speed. So how do we talk to these digital artists? There must be a specific language involved.
You're right. We communicate with GPUs using a language called GLSL, or OpenGL shading language.
Hmm.
Don't let the name intimidate you. Once you grasp the basics of GLSL, you can use it for a wide range of applications, from interactive art installations to web design, not just video games.
So it's like learning a new language that unlocks a whole world of visual possibilities, not just for video games, but anything on a screen. Now, I noticed the book dives right in with a Hello World example, but instead of printing text, it fills the entire screen with magenta.
Ah, yes, a classic. It might seem simple, but this example introduces some core GLSL concepts that are crucial for understanding how shooters work.
So even something as basic as a solid color screen can teach us a lot about the underlying structure of shaders. I'm intrigued. What kind of concepts are we talking about?
For instance, we have the main function, which you'll find in most programming languages. This is where the action starts, the entry point for our shader. Then there's GL frag color. Think of this as the paint bucket that holds the final color for each pixel.
Okay, so it's within that GL frag color that we specify the exact color we want, right? In this case, magenta for our hello world.
Exactly. And you might notice that the color is defined using something called a vec4. What's important to remember is this highlights how shaders give us fine-grained control over each pixel's color, down to how much red, green, and blue light it emits, and even its transparency.
That's incredible. Even this simple example shows how much power and precision shaders offer compared to traditional programming. So if this is the starting point, how do we move beyond just setting a solid background color? How do we start sending more complex information to our shader?
That's where uniforms come in. They act as bridges between the CPU and the GPU, allowing us to send dynamic data to our shaders. It's like having a direct line to those artists in the studio, giving them real-time instructions and information to work with. Think of it like this. You can equip your artist with different brushes, paints, or even reference images to guide their work.
So instead of being limited to a static image, we can create dynamic visuals that change based on things like user input or even the passage of time. That's amazing.
Exactly. And the Book of Shaders uses a few common uniforms that open up a world of creative possibilities. For example, there's U-time, which, as you might guess, keeps track of time.
That's got to be essential for any kind of animation or visual effect that changes over time.
Precisely. Then we have U-resolution, which provides the shader with information about the screen size. This is crucial for making our visuals resolution independent so they look sharp on any display.
So you don't have to worry about things looking distorted or pixelated if someone views them on a different device. That's really helpful.
And then there's U-mouse, which tracks the position of the mouse cursor. This is where things get really interesting, because now we can create shaders that respond to user interaction. Imagine moving your cursor across the screen and watching as the colors shift and swirl in response.
It's like we're breaking down the barrier between the viewer and the visuals, turning them into active participants rather than passive observers. I'm really starting to grasp the potential of shaders now.
And we've only just scratched the surface. The book then delves into some fascinating concepts like shaping functions. Think of them as the tools that give our code real artistic flair.
So if uniforms are like giving instructions to our digital artists, shaping functions are the brushes and palettes they use to express themselves.
A very apt analogy. These functions allow us to control values in a nuanced way. Much like an artist controls the pressure of their brush or the blending of their paints, we can create sharp transitions like a line drawn with a ruler using the step function, or achieve smooth, gradual changes like a gradient with the smooth step function.
I can see how that level of control would be essential for creating things like realistic lighting effects or textures that mimic different materials.
And there's a whole world of mathematical functions at our fingertips, each offering unique ways to shape and mold our visuals. We can use POW to create curves, exponential growth, or even trigonometric functions like sin and cos for those mesmerizing wave-like patterns.
It's like we're not just coding anymore, but composing a symphony of mathematical functions that create a visual masterpiece.
That's a great way to put it. And when you apply these shaping functions to colors, things get even more interesting. The Book of Shaders spends quite a bit of time exploring how colors behave in this context.
That makes sense. Color is such a fundamental element of visual design, and I'm sure shaders offer a whole new level of control over how we manipulate and perceive it.
You're absolutely right. One important concept the book highlights is the idea of different color spaces. Most people are familiar with RGB, where colors are defined by their red, green, and blue components.
RGB, yeah, like the settings on my TV.
Precisely. But in the realm of shaders, we often work with other color matrices like HSB, which stands for hue, saturation, and brightness.
I'm not as familiar with HSB. What's the advantage of using that over RGB?
HSB can be a more intuitive way to think about color, especially for artistic purposes. Hue is essentially the color itself. Saturation refers to the intensity of that color, and brightness indicates how light or dark the color appears.
So instead of adjusting red, green, and blue values, which can feel a bit technical, HSB lets us think more directly about the qualities of the color itself.
You got it. And the Book of Shaders demonstrates how to seamlessly convert between RGB and HSB within our code using functions like HSV to RGB and RGB to HSV. This allows us to leverage the strengths of each color model depending on the effect we're trying to achieve.
That's really helpful. It's like having different sets of tools for different aspects of our visual design.
Exactly. And here's where things get really fascinating. Remember we talked about how vectors can represent both colors and spatial coordinates?
Yes, that really blew my mind. I'm still trying to wrap my head around how something can be both a color and a position in space at the same time.
It's one of the things that makes shaders so powerful. And when we combine this concept with HSB, we unlock even more creative possibilities.
I'm all ears. Tell me more.
Well, HSB is often visualized as a color wheel, right? With hue represented as the angle around the wheel, saturation as the distance from the center, and brightness as the vertical position.
Yes, I've seen those color wheels before. They're often used in art classes to teach about color theory and mixing.
Exactly. And this is where the connection to polar coordinates comes in. Remember, we can use vectors to represent points in space using polar coordinates, just like we use them to describe points on a circle using an angle and a radius.
Okay, I'm starting to see the connection here. Are you saying that we can manipulate colors in a shader using the same principles we use to plot points on a circle?
Precisely. By converting our Cartesian coordinates, x and y, to polar coordinates, angle and radius, we can create stunning color gradients and effects that mimic the way colors are arranged on a color wheel.
That's amazing. So we're essentially tapping into the inherent geometry of color itself.
Exactly. And this is just one example of how the Book of Shaders encourages us to think differently about color and explore its full potential in our code.
I'm mind blown. This is so much more than just writing instructions. It's like we're unlocking the hidden language of visual design.
That's the beauty of shaders. They bridge the gap between technical execution and artistic expression.
So we've explored how to manipulate colors, but what about actual shapes? How do we go beyond just filling the screen with a solid color and start creating more complex forms?
That's where the concept of distance fields comes into play. Imagine you want to draw a circle on the screen. Instead of outlining the perimeter, we can actually define the circle based on how far each pixel is from its center.
So instead of drawing the outline, we're defining the shape by its interior space. That's an interesting way to think about it.
Exactly. If a pixel falls within a certain distance from the center, we color it in. Otherwise, it remains blank. This might seem like a roundabout way to draw a circle, but it offers some incredible advantages.
Like what?
Well, for starters, it's incredibly efficient. Calculating distances is a relatively simple task for a computer, even across thousands of pixels.
So it's faster than drawing pixel by pixel.
Exactly. But the real beauty of distance fields is their versatility. We can use them to represent all sorts of shapes, not just simple circles. Imagine you want to create a more complex form, like a star or a polygon. With distance fields, we can combine multiple shapes by simply adding or subtracting their distances. For instance, we can create a crescent moon shape by subtracting the distance field of a smaller circle from a larger one.
That's incredible. So we're essentially sculpting shapes out of code using mathematical operations on distances. It's like digital clay.
A fantastic analogy. And the applications of distance fields extend far beyond simple shapes. They're used extensively in font rendering to create smooth, scalable outlines for letters, and in 3D graphics for advanced effects like shadows and ambient occlusion.
Wow, I never would have guessed that something as seemingly simple as calculating distances could be so powerful and versatile.
It's one of the fundamental building blocks of modern computer graphics, and understanding it opens up a whole new world of possibilities for creating stunning visuals with shaders.
This deep dive has been incredible. I feel like I've gained a whole new appreciation for the complexity and creativity behind the visuals we see every day.
And we've only just scratched the surface. There's so much more to explore in the Book of Shaders and beyond.
Like what? Give me a taste of what other wonders await. Well, you did mention earlier that the book touches on things like creating repeating patterns and using randomness to make textures look more organic. I'm dying to know more about how those work.
Ah, yes, those are some really fun techniques. Imagine creating intricate patterns like those found in mosaics or textiles, all generated by a few lines of code.
That sounds incredible. I always assumed those kinds of things were painstakingly crafted by hand, pixel by pixel.
While that's certainly one approach, shaders allow us to define the underlying rules and let the computer generate the details for us. We can create patterns that repeat infinitely in any direction, or even introduce subtle variations to make them look more natural and less machine-made.
So it's like setting up a system with certain parameters and then letting the shader run wild within those boundaries.
Exactly, and that's where randomness comes in. By incorporating elements of chance into our code, we can create textures that have a more organic, unpredictable feel, like the grain in wood or the surface of a rock.
It's amazing to think that we can mimic those kinds of natural effects using pure math and code. Are there any other areas that the book explores?
Well, towards the end, it touches on the world of image processing with shaders. This is where things get really meta, because we can actually apply shaders to manipulate existing images, much like we'd use filters in photo editing software.
So instead of creating images from scratch, we're taking something that already exists and transforming it in real time using shaders. That opens up a whole other realm of creative possibilities.
Absolutely. We can create vintage-looking filters that mimic the look of old film stock, add blur effects for a cinematic feel, or even distort and warp images in surreal and abstract ways.
This has been eye-opening. I feel like I've barely scratched the surface of what's possible with shaders.
And that's the beauty of it. There's always something new to learn, a new technique to master, a new way to push the boundaries of what you thought was possible.
You've definitely sparked a fascination in me. I can already tell I'm going to be spending a lot more time exploring the world of shaders.
Yeah.
Thanks for being such a fantastic guide.
My pleasure. It's been a joy sharing my passion for shaders with you. For anyone listening who's ready to dive in themselves, remember, don't be afraid to experiment. Start with the basics, explore the examples in the book, and see where your creativity takes you.
Great advice. And who knows, maybe we'll have some listeners creating their own mind-blowing visual effects soon. That's all the time we have for today's deep dive into shaders. Until next time, keep those pixels colorful.